Let's say we're trying to calculate the limit as x approaches a of f of x. In this case, f of a isn't defined, but we can look at what happens as we get close to a. So you could think about what happens to a as we approach from the left, think about what happens to a as we approach from the right, and those are really the only directions we can think of because, well, our inputs, the inputs to our function are one-dimensional. Our input is given by the x-axis, that's just a line. So our inputs are one-dimensional. So we can only approach a from the x-axis, from along the x-axis in some direction. Now, let's say we were instead looking at a multivariable function. I'm not going to be able to do a great job of drawing this, so I will encourage you to use your imagination. So let's say we have an ordered pair. Usually 0, 0 is what we're interested in, but that might be a little hard to draw in this case. So we'll say we have a vector here, a vector xy, or we'll call it AB. And let's say we have some really fancy function that's defined for all these different places, but right at AB, there is some sort of hole. So it's defined everywhere else, but there's a hole at AB. Now, we might try to do the same thing. Think about what happens to the function as we get closer to A, our ordered pair AB, but now there's a lot of different ways we can get to AB. We might approach it from this direction. We might approach from both sides. We might approach it along a totally different line. Try to find that. We might even try to approach it along a curvy line that does something like this. And all of those are different ways to approach the value AB. And it turns out that this is going to make it a little bit harder to define and especially to calculate limits when our inputs have multiple dimensions. So the first thing we're going to do is define what exactly we mean by our limit in multiple dimensions.